Hey guys, welcome back. We are looking at 6-2, day 2. 6-2, day 1 was multiplying rational expressions. Looking what happens when we multiply things with square roots and cube roots. Today we're going to look at dividing rational expressions. All right, so let's get into it. There's going to be a lot of at least start off with similarities here between multiplying and dividing. Okay, so if we are combining radical expressions when we're talking about quotients, again, quotients is just answers to division problems. So that's what we're talking about. If I am combining radical expressions by dividing, just one thing that you have to keep in mind, that if I have the nth root of A divided by the nth root of B, then that is the nth root of A divided by B. All right, so what all does that mean? So first of all, just a couple things to notice here. The indices have to be the same. So both square roots, both cube roots, both fourth roots, whatever. All right, and if they are, if I have a division problem involving two different square roots, for example, I can write that as a division problem underneath one square root. Or if I have a division problem involving two cube roots, then I can write this as a division problem underneath one square root. All right. So let's look at how we can apply that. Again, we'll probably do these two examples. I'll save that one for you to do on your own if you'd like, but should be pretty similar to these top two. All right. So again, key thing to notice here is we're talking about two square roots. All right. If this were a square root and this were a cube root, I couldn't do anything with this problem. But since they're both square roots, all right, so here's my A and here's my B. What that means, or what this property tells us, is I can write this as one square root with a division problem inside. All right, so I get the square root of 18x to the fifth over 2x cubed. And now order of operations, this is like a grouping symbol. I can do the stuff underneath the grouping symbol here. So I can do 18 divided by 2, all right? That's 9. I can do x to the fifth divided by x to the third. Those properties of exponents that we looked at on page 360 says I can subtract these because they've got the same base. So that'll be x squared. Now, still got the square root around that, all right? Haven't done anything with the square root yet. Okay, so I've got the square root of 9x squared. And now, go back to kind of day 1 here. If I've got a product, I can rip this apart. So I can look at this as the square root of 9 times the square root of x squared. Some of you might not need to do this middle step. I like to do it just to kind of keep things, in line here. The square root of 9 is 3. And the square root of x squared is, remember, it's the absolute value of x. If this index is an even number, you need those absolute value symbols. All right. So this thing simplifies as 3 times the absolute value of x. Again, same thing. Now this one is dealing with cube roots, but again, I'm talking about two cube roots. So that means I can write this thing as 162y to the fifth divided by 3y squared. And one big cube root, I can do the cube root of that division problem. Again, here this is a division problem involving two different cube roots. Now this is a cube root of a division problem. All right, that's just using this property with that as A and that as B. And now I can look and see what I can do. 162 divided by 3. We learned the other day, is this divisible by 3? Let's see, 1 plus 6 is 7. Plus 2 is 9, and 9 is divisible by 3, which means this is divisible by 3. 162 divided by 3. I'm going to do this without a calculator. I'm also doing this lesson without a net. All right, so I know that I'm taking my life into my own hands, but I am willing to do anything for you guys. All right, so 162 divided by 3. 3 goes into 16 5 times with 1 left over, and then 3 would go into 12 4 times. So I get 54. And again, y to the 5th divided by y squared. I'm dividing things with like bases. I can subtract their exponents. So that's y cubed. So I get the cube root of 54y cubed. Okay, now I can, this is a product, I can rip it apart into 2 different ones. So it's the cube root of 54 and then the cube root of y cubed. All right, cube root of 54. A number times itself 3 times, it gives you 54. I'm not aware of one, but does 54 have any factors that are perfect cubes? Again, let's look at our perfect cubes. 1 times 1 times 1 is 1. That's a boring one. We don't look at that. 2 times 2 times 2 is 8. 8 doesn't go into 54. 3 cubed. 3 times 3 times 3 is 27. Yep, 27 goes into 54. So I can rewrite this as the cube root of 27 times the cube root of 2. And then the cube root of 27 is 3. And then the cube root of 2, we don't know what that is, so we just leave it the cube root of 2. So the cube root of 54 I can simplify to 3 times the cube root of 2. Now the cube root of y cubed. Now remember, we talked about this a little bit. The little trick here is you could just divide those exponents. So that's y to the 1st, or just y. And now here, I don't need the absolute value symbols because that's an odd index. You only need those absolute value symbols when you're talking an even index. And again, when that's a square root, if there's nothing there, that's assumed to be a 2. So now I can kind of rearrange things, and I can write this as 3y times the cube root of 2. Just be careful as you're writing this that it doesn't read y cubed. I mean, if you start sliding those 2 close together, just be careful as you're writing that so that this index doesn't look like an exponent for that y. All right, so we can simplify division problems. Okay, what if we're looking at this, and again, I'm going to zoom in just a little bit there. Okay. No, I'm not. I'm just kidding. So that is 5x squared over 12y squared z, the cube root of that. Well, how in the world do I do this? Because, it's not like the others. 5 doesn't divide by 12, and there aren't any common bases there as far as my variables go. Well, this is where we want to do what's called rationalizing the denominator. Okay? And rationalizing the denominator is writing an expression so that there are no radicals in the denominator. Okay, so if we want to rationalize a denominator, again, it simply means let's write that expression so that there aren't any more radicals in the denominator. All right. So how do I go about rationalizing this denominator? Okay, so the first thing I can do is I can split this up. All right, so that is the cube root of 5x squared over the cube root of 12y squared z. Okay. So now, if I want to rationalize this denominator, okay, if I want to get that radical outside of the denominator, okay, what I can do is I want to multiply this thing by 1. All right, so watch what I'm going to do here. I'm going to multiply. Now again, multiplying by 1 doesn't change it. Watch the form of 1 that I multiply this by. The cube root of 12y squared over z. And the cube root of 12y squared over z. And I'm going to do that one more time. The cube root of 12y squared over z over the cube root of 12y squared over z. Okay, now what did I just do? Let's take a look at this. Okay. Now, the first thing I need you to understand is we are just multiplying by 1. All right. This is, 1 can be 8 over 8. It can be negative 2 over negative 2, or it can be the cube root of 12y squared over z over the cube root of 12y squared z. All right. This is just multiplying it by 1. So I'm taking this thing and multiplying it by 1 and then multiplying it by 1 again. Let me put my line in there. All right. And so I'm not changing this thing. Okay. But why did I do that? Well, let's look at the bottom. If I take, let's go back here. If I do the cube root of 8, I'm just making this up. All right. This really, this number doesn't have anything to do with those. If I multiply the cube root of 8 times the cube root of 8 times the cube root of 8, look at what I get. Again, I could write this as the cube root of 8 times 8 times 8. Or I could write it as the cube root of 8 cubed. And the cube root of 8 cubed is just 8. If I multiply a cube root by itself 3 times, I get the radicand. I get just what's ever under there. So if I take this cube root times itself 3 times, okay, I'm going to get in the bottom here just 12y squared z. I'm going to get whatever the radicand is. Okay, so why did I do that times itself 3 times? Because that was a cube root. If this would have only been a square root, I only would have had to do it 2 times. If this would have been a fourth root, I would have had to have done it 4 times. All right, but take a look at what I've done. I now have no more radicals in the denominator. All right. And so now I've taken care of that problem. Now let's look at what's going on up here. Now again, I'm going to kind of skip some steps here, but these are, first thing to catch is these are all cube roots. So I can multiply these, and I'm going to multiply the numbers. So I got 5 times 12 times 12. All right. So 5 times 12 is 60. And then 60 times 12, I think, is 720. I've got x squared. Yep, that's it, just x squared. I've got y squared times y squared, so that's y to the 4th. Didn't quite leave myself enough space here. And then I've got z times z, that is z squared. Now that is still underneath a cube root. All right, if I do a cube root times a cube root times a cube root, I get another cube root. Now again, this didn't all cancel out like I did here because this one's not the same. Okay? So now, all right, this is okay. I've gotten rid of the radical in the denominator, but can I simplify this at all? Does 720 have any factors that are perfect cubes? Well, let's go back. I'm going to go back to my list here. Let's see. 2 cubed is 8. Does 8 go into 720? I think it does, all right, because 8 goes into 72. All right, so I'm gonna write that. I'm gonna kind of take my time here, all right. So I'm simplifying this. So I'm gonna write that as the cube root of 8 times the cube root of 90. Okay. Now, what about the cube root of x squared? I really can't do much with that, all right? Because again, if this was if this was a 3, I could do 3 divided by 3, but I really can't do much with the cube root of x squared. And similar thing, I know I'm doing a little bit out of order, but I really can't do much with the cube root of z squared. Now the cube root of y to the 4th, since this is bigger than 3, I can find a factor of y to the 4th. I can find an exponent, that. Or let me go back to the first thing I was going to say. I can find a factor of y to the 4th that is a perfect cube, namely y cubed. And then I've still got y to the 1st. Okay, because again, when I multiply these two, I add the exponents. All right, and 3 plus 1 gives me 4. I couldn't do anything with these two because they're both less than 3. So they're now x squared. I could have done x times x, but neither one of those is a cube root. So I really can't do much there. Okay, and now that whole mess is still over. You ready for this? 12 y squared z. Phew. Now let's start simplifying this. So the cube root of 8 is 2. Cube root of 90 I can't do anything with, so I'm just going to leave that as the cube root of 90. The cube root of z or of x squared, I already said I can't do anything with. The cube root of z squared, I can't do anything with. The cube root of y cubed is y. Don't need any absolute values because that's a perfect cube. And now I've got the cube root of y, which I can't do anything with, so that's the cube root of y. Now, real quick, I just want to look at this. Are there any factors of 90? Well, again, I'm sorry. That is still over 12 y squared z. Few. Now, cube root of 90, does 90 have any perfect cube factors? Let's go back here. Let's see, 2 cubed is 8. 8 doesn't go into 90. 3 cubed is 27. 27 doesn't go into 90. 4 cubed, 4 times 4 times 4 is 64. 64 doesn't go into 90. If I go to 5 cubed, 5 times 5 times 5, I'm bigger than 90, so nothing else is going to go into 90. So that's in simplest form. So now I'm ready to multiply. Let's see, the stuff outside the radicals, I get 2 times y. And all the stuff underneath the radicals, I can write it because they're all cube roots. I can write it under 1 cube root. The cube root of 90, x squared, z squared, y. Or I might write x squared, y, z squared. Usually put those in alphabetical order. Phew, over 12 y squared z. We're almost there. The last step, that 2 and that 12, if you think of the fraction 2/12, that's the same thing as 1/6. Now, I can't do any canceling here because this is underneath a cube root and this is not. All right. But what I can do is these y squareds can cancel. 2 of these y's can cancel out 2 of those, leaving just y to the first. Again, if I had y times, again, well, both underneath the radical, let's do this. Both outside the radical, I can subtract those exponents, so 3 minus 2 is 1. So here's what I get. Here is my simplified version. Y times the cube root of 90 x squared y z squared. There I go. I put it in alphabetical order. Over 6. Ay, ay, ay. There we go. All right. Holy cow, that's a lot of steps. Okay. But again, this idea of rationalizing the denominator, we took this thing. This expression here is equivalent to this expression. And it's in simplest form. There's no more perfect cube factors I can take out of there. And I don't have a radical in the denominator anymore. Okay. All right, so just these four questions. Now, what I would like you to do, since this is all part of 6-2, all right, what I would like you to do is take your day 1 6-2 and your day 2 6-2 and just combine those in one big assignment. I'm just going to grade that once or put that in as one assignment on Progress Book. I just want you to share that as one assignment on Flipgrid. All right. So the problems from day 1 6-2, which I'm trying to find right now. All right. So these problems, and just attach these right onto the end of it, and just share that as one assignment in Flipgrid, and you're only going to see that as one assignment in Progress Book. All right. Let me know if you have any questions, guys. I'll be more than happy to help you out with this. All right. Good luck. Take care.